Hey folks, this is Asif, your host for today. And thank you so much for joining us on this AI research show. And with me, we have our research team, consists of Luca and Ikram. And we will start our presentation today with Luca. So let me bring Luca on the screen.
Okay. Hi, everyone. Can you see my screen? Asif, can you see my screen? Let me know if I can start, Asif.
You can start, Luca.
Can I start?
Yes, that's great.
Okay, thanks. Hi, everyone. I'm Luca Rotta, a PhD student at the University of Milan, and I'm a research consultant for Market Post. And today we are going to talk about a survey on contrastive self-supervised learning. The authors of this paper come from the Department of Computer Science and Engineering of the University of Texas at Arlington in USA. If you have any comments during my presentation, you can put your comment on the chat and then I will answer you after the presentation. So nowadays, we all know that deep learning methods are used to face most of the existing computer vision tasks, for example, image classification or object detection. And these happen because deep neural networks are able to automatically extract meaningful features from the raw data that we provide them. For example, in the case of computer vision tasks, these data are images. But what are features? Features are those characteristics that are crucial to perform the computer vision task that we are considering. For instance, a possible computer vision task is image classification. And in this case, for example, we can determine what type of car is contained inside an image. And in this type of task, we need to extract the features like the size of the car, its color, its shape, and the wheels, because this information is important to determine the type of car contained inside the image. And typically, computer vision tasks are performed by using supervised learning solutions. In this scenario, we have these training images that contain different types of cars, and each image is associated with the corresponding class of that image. And this is needed because the deep neural network that will extract features from these images, and then it will find correlations between the image and the corresponding class to perform the classification. Indeed, the first layers of the neural network are in charge of extracting the features from the images, and then the features are used to perform the classification of the images. The main problem of supervised learning is that it heavily relies on huge amounts of labeled data. But the problem is that the manual annotation of data is a time-consuming, expensive, and error-prone process. And for this reason, the researchers started to investigate and find alternative approaches that can rely on the huge amounts of available unlabeled data. So the idea is that to use the unlabeled data that we have in the real world to learn our task. And for this reason, today we are going to talk about self-supervised learning, whose goal is to automatically extract meaningful features not from labeled data, but from unlabeled data. And this is possible by automatically creating self-defined pseudo-labels that are used as a supervision during the learning process, as we will see later. And the focus of the survey we are going to talk about today is indeed contrastive self-supervised learning. Let's see an overall framework for self-supervised learning. We have the available unlabeled images coming from the real world, for example, and our goal is to perform image classification on these images. For example, we want to recognize if an image contains a bird or a cat or bananas, for instance. Our problem is that we don't have enough labeled data to learn this task in a supervised way. In self-supervised learning, we can have, for example, we can use an existing data augmentation technique to create a transformed version of the original images. For example, if we see the image of the bird, we can apply rotation to obtain a transformed version of this image. Then, when we have the transformed version of images, we can provide them to the deep neural network that in this case is called encoder. And since we are dealing with images, the encoder in this case is a convolutional neural network. Now we have to invent a fake task that is called a pretext task that is useful because the encoder will have to extract meaningful features for this task, but at the same time we have to choose a pretext task so that these features will be also useful for our main task, which is image classification. And since here we have rotated versions of images, a possible idea for the pretext task is to predict the rotation degrees applied to the rotated images. So in this case, we can assign pseudo labels to the transformed images. In this case, the case of the bird, we have a rotation applied with 90 degrees, and so the pseudo labels will be 90 degrees. And then encoder will extract the features to predict the rotation degrees. And so, for example, the possible feature is the shape of the animal, because thanks to the shape, we can understand the rotation degrees applied to the original image. But at the same time, you can understand that the shape of the animal is also useful for our main task, because thanks to the shape, we can detect and distinguish a bird rather than a cat, for example. And indeed, the idea is that now we can use the encoder that is able to extract these features, not only for the pretext task, but also for our main task that is called, in this case, in self-supervised learning, this task is called downstream task. So if we have novel images that we can provide to the encoder will extract those features like the shape of the animals, and then we can detect if the animal is a bird, a cat, or a dog, because these features are useful also for the downstream task. Typically, we can also enhance these features because maybe we have some few examples of labeled images for a certain data set, and then we can use these labeled images to enhance the features extracted by the encoder for our downstream task. Let's move back for a moment, because now we have to add the contrastive learning to this pipeline, to this framework. The goal of contrastive learning is to enhance the feature extracted by the encoder, and this happens because the contrastive learning approach forces the feature representations of similar images to be close in the feature space, and at the same time, it pushes away the feature representations of non-similar images in the feature space. And typically, we can use the augmented images from the pretext task to perform contrastive learning. The idea is that now in the feature space, we'll have a more convenient representation of the features, because the features of the same animals are close in the feature space. So it will be easier to detect that animal for our main task. This is an example of contrastive learning in which we can create positive pairs of images, in which we have the original image, for example, the image of the bird, and the corresponding transformed image, the rotated version. And you can see that the features extracted from the positive pairs or the positive pair images will be attracted in the feature space, while at the same time the feature extracted from different images will be pushed away, will be distant in the feature space. And so in this way we have an enhanced version of the features. In contrastive learning, the pretext task consists of the data augmentation technique that we decide to apply to the original data. And the encoder will learn some features that will be invariant to a specific characteristic based on the chosen pretext task. So it is very important to choose the right pretext task based on our main goal. And thanks to contrastive learning, instead, the encoder will also learn to find similarities between different representations of the same image. In this paper, in this survey that we are presenting today, the authors distinguished between 4 different categories of pretext tasks: color transformation, geometric transformation, context-based, and cross-modal based. Let's see color transformation first. This task involves changes in the color levels of the original images. For example, we can apply blurring, color distortion, or conversion to grayscale. And thanks to this kind of pretest tasks, the encoder will learn to recognize similar images invariant to their colors. With geometry transformations, instead, the geometry of the original image is modified without altering its pixel information. So we can apply techniques like transformations like scaling, cropping, resizing, rotating, or flipping. Considering the cropping technique, which is applied in the B image, the encoder will learn to recognize the local views of the same image in this way. Considering instead context-based pretext tasks, we have two examples in this survey. We have the jigsaw puzzle, whose goal is to identify the correct position of the different patches of the original image. And in this way, the encoder will learn information about the spatial context of the original images. Another example of context-based task is the frame order-based approach, in which, for example, we can try to reorder the shuffled frames of a video during the pretext task. And in this way, the encoder will learn visual representations in the feature space, because we are still dealing with images because we have frames of a video. But at the same time, the encoder will also learn information about the temporal coherence of the video, because it has to understand how to reorder the shuffled frames of the video. The last task that we are going to see is the cross-modal based approach, that is also called the view prediction, because it is useful when we have data with multiple views. In this example, we can see that the same object is represented from different perspectives. The idea is that during contrastive learning, we can force simultaneous viewpoints to be close in the feature space, while the frames at the different time instants, like the blue one and the red one, are forced to be distant instead in the feature space. And in this way, the encoder will learn to recognize objects from different perspectives, thanks to this pretext task. Okay, let's see now some few results that have been shown in this paper. We can see that the top one accuracy obtained without any fine-tuning technique is close to the top one accuracy obtained by supervised approach. This means that a supervised deep neural network has been trained on the ImageNet dataset, and then instead we have also trained some self-supervised approaches without any labeled data, and we have similar results considering top one accuracy. On the right, instead, we can see that the top 5 accuracy obtained with fine-tuning applied with the self-supervised solution on few labeled examples significantly outperforms the one obtained by a supervised solution. In this case, this means in this row, we can see that the supervised solution have been trained only on 1% or 10% of the labeled images of the ImageNet dataset, and it reaches about 56% of top 5 accuracy, while self-supervised approaches that have been fine-tuning only on these low percentages of labeled data reaches very higher recognition rates. Finally, this is the last result that we can see. We can see that contrastive learning performs better than supervised learning when it is tested on a different dataset. In this table, we can see that supervised solutions that has been pre-trained on the ImageNet dataset and then tested on the Places dataset reaches about 53% of top 1 accuracy, while contrastive learning that has been trained on the ImageNet without any fine-tuning on Places reaches slightly higher recognition rate. That was all for this survey. I hope that you enjoy it. And I remember you that if you have any comments, you can put them on the chat, and then I will answer you later. Thank you very much for your attention.
Thank you so much, Luca. It was a really wonderful presentation, and we hope our audience loved it. And guys, if you have any questions or if you have any comments on the presentation, feel free to put it on the comment side, whether you are on YouTube, LinkedIn, or Facebook, and we will try to answer it ASAP. Now, thank you again, Luca. Now, moving towards our second presentation, it's a very interesting one, and the presenter is Ikram, our research consultant from Austria. And yeah, without any delay, let's get him on board here. And yeah, hey Ikram, welcome.
Thank you. Yeah, thank you for the kind introduction. Yeah, so I will be talking about the real-time single image and video super resolution using an efficient sub-pixel convolutional neural network, which is a research paper from Twitter, and you can see the archive link there if you want to learn more about it. And yeah, so hello there. Here's a brief introduction about myself. I'm a PhD scholar, a PhD student in Alpine University at Klagenfurt. I'm working on the Athena laboratory as a video coding and deep learning topics, and I am a research consultant in the Contextbased. So let's start with our presentation. So this will be the brief agenda we'll be following today. Introduction, we will introduce what is super resolution, and in the related work parts, we talk about existing solutions in the literature, and then we introduce the star of the night, which is the ESPCN, and then we talk about results before we conclude the paper. So let's start. So we can define super resolution as the task of extracting high resolution images when we only have the access to the low resolution counterpart. And we want to do this operation as smooth as possible, and we want to keep the high resolution image as close to the original version as much as we can. Since this is a lossy process because we lose some information when we go from a high resolution to the low resolution, reversing it is a bit problematic. So we want to preserve this lost information as much as we can. So there are two different problems when it comes to super resolution. First one is the multi-image super resolution. Here we have multiple low resolution images of the same scene. They are captured from different perspectives so that we can exploit these redundant information between different views. But this will not be the focus of our paper today. Instead, we are more interested on the single image super resolution problem where we only have a single image and we want to extract a high resolution version of it using that information within the image itself. So in this case, we only have the information available within the image. And so we need to find a way to use this information. And there are some traditional methods like bilinear or bicubic interpolation that are used to achieve the super resolution task. And let's just jump into the bilinear interpolation here. It's actually pretty straightforward. So if we assume that we are upscaling by a factor of 2, we prepare 4 pixels for each pixel in the low resolution image. And then we move these pixels to the corners. And then in between, we just linearly interpolate the pixel values. Of course, this is producing some results, but we will have some artifacts, so we would like to avoid this as much as we can. And binary interpolation just works fast, but it gives us some visually unpleasant results. So let's see how it is done in the literature, this single image super resolution problem. So when it comes to that, we actually have 4 groups of methodologies. The first one is the edge-based single image super resolution. Here, the prior information is extracted from edges in the image, so we can get really high quality edges in the high resolution image. But while doing that, we do some texture information, so the resulting image has some poor textures. The second group is the patch-based approaches. Here, the mapping function between the low resolution and high resolution image patches are learned, and usually these mapping functions can be like single support vector regressor or Gaussian process, etc. Third, we have the image statistics-based approaches, and these methods try to exploit the generic image properties. And they try to model the distribution of pixel values using something like gradient distribution or using the total variation information among the pixels. And finally, we have the sparsity-based approaches. These work in the transform domain instead of the pixel domain, and they do the sparse coding in the transform domain. So the goal here is to learn dictionary of image atoms in transform domains and use that dictionary to extract the high resolution version of the low resolution image. I mean, these methods worked well, but their time has ended when the deep learning saga began, as with many application domains nowadays. So in the super resolution with deep learning parts, we have some studies that are done before ESPCN that actually inspired the authors to come up with this solution. So in these approaches, the image representation is derived via neural network, and that means that we need to train the network with very large image data sets. So that is one thing that we need to always keep in mind when we talk about deep learning approaches. So the goal here is to learn nonlinear mapping of low resolution and high resolution image patches or images directly. And the first DNN method that achieved a superior performance in the super resolution task was the SRCNN, which was released 2 years before ESPCN. And that was a pure CNN-based approach. And after the release of SRCNN, the acceleration in the super resolution field using deep learning methods speed up a lot. But why do we need SPCN? So the first reason is the superior performance of CNNs comes with a cost, which is the high computational cost. And there needs to be something done in order to use these methods in the practical scenarios. And this high computational cost is mainly caused due to the upscaling that is done before the CNN structure begin. And this is how SRCNN does. The first, it upscales the image to the target resolution using bilinear or bicubic upsampling. And then using the CNN, it just tries to remove the artifacts from the images slowly and slowly. But this is causing too much computational complexity. So the goal of SPCN is actually to target this high computational complexity while also improving the performance of super resolution. There are two main contributions of the ESPCN paper. The first one is moving the upscaling layer, upscaling operation towards the end of the network. So this results with reduced computational and memory complexity and opening the room for practical applications. The second and more important one is the sub-pixel convolution layer. This is how they manage to move the upscaling operation towards the end of the network. And this layer learns the interpolation operation implicitly and achieves far more superior performance compared to using a traditional upscaling method. Here's a brief overview of the SPCN. So as I mentioned before, SRCNN uses the upscaling before they pass the image to the network. So the upscaling is done on the low resolution domain, but the whole network is worked with in the high resolution domain. Due to that, it increases the complexity a lot. So ESPCN, instead of that, applies almost all operations in the low resolution space throughout the network, which can save a lot of time and the memory, and then applies the upscaling towards at the end using the sub-pixel convolution layer. And we can see the overview of the ESPCN network structure here. Now let's jump into the sub-pixel convolution layer, which is the key contribution of the ESPCN. So this layer is applied at the end. So it's the output layer of the ASPCN. So the layer before sub-pixel convolution will have C times R channels. Here, the R is the upscaling factor and C is the number of input channels. So if we have an RGB image and we would like to upscale it by 2 times, the number of channels will be 3 times 2 times 2, which is the 12. And then we apply sub-pixel convolution, which is a 2-step operation. The first, we apply the convolution operation, and then we rearrange the pixels. So the convolution here is applied with a stride of 1 divided by R, which is actually combining each pixel in different feature maps to R times R square area in the high resolution image. And since this upscaling is done via a convolution layer, the interpolation filter is learned implicitly by the network, which can give us a far more superior performance compared to the other way. So let's see some results. And we can see the PSNL results of different methods in different data sets here. And as you can see, ESPCN achieves the best performance in almost all our data sets. And this is, in fact, true when we train the ESPCN with a large data set like ImageNet. In terms of the qualitative performance, one might not see much difference, but actually, the details are more visible within ESPCN results, like it preserves the details more, especially the edges and the texture information. But if you want to see more results, you can always refer to the paper. You can see how it looks like for different types of images. I have one more example here. For example, we can see the original image on the left, which is the ground truth high resolution image. And in the middle, we see the image upscaled with the SRCNN. We can, when we zoom into the a cheek of the baboon, we can see it has some blurry artifacts, like the hairs are not clearly visible. This is in fact slightly true for ESPCN as well, but we can see more sharper details here, like it is producing more visually pleasant results when we zoom out and take a look at the image at once. So this is actually impressive results, and we need to remember that ESPCN does it much faster than the SRCN. And of course, the video super resolution, which was the target of ESPCN, like why they introduced this. So here we can see, again, ESPCN outperforms SRCN in all the data sets, almost all of the videos. so it gets higher PSNR values. But for the video super resolution, the important aspect is actually the runtime, not the results itself. So when we check the runtime evaluation here, we can see the SRCN, ESPCN, which is on the top left on the graph, that gets the highest PSNR and also the lowest runtime. And when we compare it with the SRCNN, which is the network that the ESPCN tries to improve on, it can actually achieve 10 times more FPS or even 15 times. So, and the key pointer here is it's above 24 FPS, which is considered the real time in the video applications. So the SPCN can upscale 3 times with 26 FPS frames per second and 34 FPS frames per second for the times for upscaling. So this means that we can actually in practical scenarios, we can use ESPCN to improve visual quality of videos. So let's sum up today's presentation. We talked about the ESPCN, which is a method proposed for the single image super resolution. And the key contribution of ESPCN was moving the upscaling operation towards the last layer of the network to reduce the computational cost of the super resolution networks. And this is achieved by introducing the subpixel convolution layer, which learns the upscaling interpolation implicitly, so it gives better performance and manages the run much faster than the traditional upscaling factors. And these two combined give results in a significant speed and performance boost. As a future directions, the authors mentioned that they would like to focus more on the videos and they want to use the temporal information in videos. Right now, it is just using the image super resolution base, so they upscale every single frame independently, but there is a lot of redundant information that can be used between the frames. So they would like to target this information for video super resolution, and they plan to use something like 3D convolution layers. And this was all from my side. Thank you for your attention. And if you have any questions right now, you can ask them via comments or you can reach me via LinkedIn later on. And don't forget to visit our website for more interesting studies and summaries. Thank you.
Thank you, Ikram. It was really a wonderful presentation. And folks, you know what? We are bringing up another, article series, and this time from Ikram. It's on how machine learning is used in video encoding, and it's coming in the next few days, where we're going to talk about a lot of video encoding, how machine learning is involved, like how the videos are delivered, why HAS become the de facto streaming versus downloading. A lot of cool stuffs are coming up in a 6 article series on video encoding using machine learning. So Ikram has really put some time on that. And then Luca is also working on a lot of cool papers to bring up, some really cool paper summaries in writing, not just on video, in writing as well. And then like we are very open, like if you are having any questions, any suggestions, we're welcoming those as well. And feel free to reach out to me directly. I am one of the co-founders at Martech Post and CEO. So reach out to me. My email address is here. And yeah, so thank you very much, everyone. I hope you like this show. It is recorded and it will be put in on YouTube as well, so you can watch it if you missed it for any reason. And thank you again. Have a wonderful day. Take care, guys.